So now that we have the new graph, we can see what exactly. So that is the graph G that we have made, and the value of K is the same as number of groups. Okay. Now we will prove that if F belongs to CNF SAT, then this, let us call it a GF, then this is logically equivalent to GFK belonging to click. How do we prove that? So the idea is, let us prove the first direction, the implication first. So we start from here. So if F belongs to CNF SAT, then it means that there exists an assignment Okay. So what we do is, it means in every clause there is one literal according to assignment. Otherwise it would not have become one, right? So what we do is choose a vertex in GF in that group. That is each group. Okay. So if we choose a vertex labeled with one literal in each group, then we claim that there exists a click of size K in GF, which is constructed in the following manner. The set of vertices chosen above form a click. The reason being that none of them is the complement of the other. Complement of another. Why? Because they are all one. In the assignment. And they are in different groups. Implies that there is an edge between them. Why should there be an edge between them? Because that is how we have drawn the edges. This is how we have drawn edges. We have drawn all the edges possible except from vertices in the same group. Also vertices labeled with complementary literals in different groups. That has been avoided. All the others are there. So as these are all one literals, they are not complements of each other, and they are in different groups. So there must be the edge. We have drawn edges. So hence there is a click. So F belongs to CNF SAT implies that GFK belongs to click. That is, GF contains a click of size K. Then we have to prove the reverse. We have to prove that GF belongs to K belongs to click implies that F is satisfiable. How do we prove that? Now suppose it contains a click of size K. So we are given that GF has click of size k. It means that each vertex, could say g k or something, each vertex must belong to a different group because there are no edges between vertices in the same group. Also, each literal label is not a complement of another literal label. Why that has to be true? Because no edges have been made if that was the case, right? So it must be that all of them are not, each of them pairwise is not the literal label complement of another one. So we have a clique in which each of the vertices belongs to a different group and none of them are complements of each other, which means that we assign a value 1 to each of those plain literals and 0 to the complemented literals. Implies that now each of them belongs to a different group and each of them forms a 1 in that group, right? In that clause belongs to a different clause and can be assigned a 1. So every clause is satisfied. Which means that the reverse is also true. If there is a clique, then the CNF is satisfied. So that part is done now. So because CNF SAT was polynomial time reducible to clique problem, clique has been proved NP hard. Now to prove that it is NP complete, we need just one more thing. What is that? It is that we have to prove in it NP. And proving it NP is something very, very easy. It is just a clique verification in polynomial time. So we will take it that clique verification. We are given a G, a K, and a G dash. That is GK is the problem and G dash is the certificate. We have to verify that this is a certificate to GK belonging to clique. So if G dash V size is less than K, we return a no. It means that this is not a certificate. Else what we do is we make a set of vertices and for each U in P and for each V in P, what we do is we check whether UV belongs to G dot E, that is the edge set. So if it does not belong, we immediately break it up and return with a no. Now if each of them belongs, it is a clique. So we return a yes. So if this graph returns a yes, it means that it contains a clique of size k. If it returns a no, it does not mean that it does not contain a clique. It only means that the given subgraph is not the certificate to it. Now that we have proved or click problem to be NP complete, what we can do is we can use it to prove other problems to be NP complete. So if something can be polynomially reduced from click, then that becomes NP hard, right? And if that problem is then proved NP, then it becomes NPC. So that is the approach that we are going to take. So the next problem that we take is that of independent set, which is something we have done or studied about in class. So we will be knowing about the problem. And what we'll do is we'll make use of click problem. By giving a polynomial reduction from the click problem, we'll prove that independent set is NP complete. So how do we go about it? Let us quickly review the problem and go ahead. Click we have already seen. Independent set is as follows. We are given a graph G and a positive integer K. And what we have to find or what we have to look for belonging is there a subgraph G dash of G such that no pair of vertices in G has an edge between them? So a set of vertices is that there are no edges pairwise between them. Edges between them is called an independent set, as we know. And the optimization problem was maximal independent set